Oh yeah, so we have to wait for the slides. Thank you. Yes, so that's the title. I'm going to come to this question of storage efficiency and volumes for mapping, but using a very specific case of Sleipner. And I'm going to first of all thank Canadian. Ricardo Martinez just finished his PhD with us and has done this wonderful work on full waveform inversion, which I'll be using, supported by Vet Lavinia, and using their software. And it does have a bearing on this famous pyramid. Is the pyramid falling down? There have already been discussions about theoretical capacity, effective capacity, matched capacity. Maybe we should take the pyramid down and replace it with the 9-layer storage readiness levels. That would be a good idea. Should we build a new pyramid? Anyway, I'm going to talk about the matched capacity at Sleipner. What do we actually find about the capacity at Sleipner, and how does that inform the effective capacity, which is what has been used regionally for most of these assessments? And I've gone on record saying with Tip Meckel that the storage resources are overwhelmingly available. That is my personal opinion. It's a published opinion. We've mapped the entire world's sedimentary basins offshore using a gravity inversion. The red is 5-kilometer thick packages. The orange is 2-kilometer thick packages. Of course, they include some shales, but they include vast amounts of sandstones. In the dots, you see all the oil and gas fields from the Russia-Euro belt to the Middle East to the North America, Gulf of Mexico and onshore, and the North Sea. But in addition to all the prolific basins that have hydrocarbons, we have many other basins which don't have hydrocarbons. For example, West Africa, North and South America, along the eastern seaboard of the United States. So I think there's loads of storage, okay? But some people don't agree with me. So there's this famous paper published in Nature last year, which caused quite a stir, and they applied some very, very strong cutoff criteria to say that there isn't very much storage capacity. Therefore, we should focus the storage capacity on only industrial capture. And this has kind of caused a storm of reaction. There is a set of, on the social media, there's expert reactions to this study. And a group of us are also preparing a formal kind of rebuttal to this study. But to summarize, they are climate scientists who are saying, we want to put stringent constraints, practical constraints. They're not saying anything analytically, they're just saying, do some screening. And ironically, I think Renato is here, their screening criteria are so stringent that the Northern Lights project would not qualify, because it's too deep, too much water, too deep. So anyway, we'll take that discussion later. So on to Sleipner. What can we learn from Sleipner? Although Sleipner is coming up to its 30th anniversary, we still have a lot to learn. So it's a long horizontal well injecting at the base of the Utsira sandstone, and for the last decades, we've been using time-lapse seismic to track that plume and learn from it. And before I go on to the details of what we've recently done, I just want to make the point that when you look at those polygons of expansion of the plume over time, so these are the integrated footprint of CO2 expansion over time at Sleipner from 1999, the first survey, to 2020, showing how it grew. And it's basically an elongate object north-south because of the structural closure. There is some migration to the west recently, which caused a bit of a local stir. But macroscopically, the expansion of the plume has stayed within the 3-kilometer radius predicted before the study started in 1996, okay? They went on record saying, we do not expect the plume to go more than 3 kilometers in any direction. And that's exactly what happened. So I would be controversial first. The plume has behaved exactly as expected, okay? Of course, as the project proceeded, we learned all these little details about what actually happened, and those details are fascinating. So what we've been doing in the last 3 years is looking at full waveform inversion of this seismic data. Full waveform inversion is a way of using all the seismic imaging data and all of the transiting waves through the object to invert a velocity model. So on the left-hand side, you see the velocity model from the 2010 survey, where you can see in the purple colors, which is the lowest velocity, about 1,500 meters per second, that is where the CO2 is. And you can see all 9 layers. And you can also see, yeah, we do have a pointer. We can also see several of these feeder systems which connect the layers. And for the last 20 years, those mystery feeders have also been a much debate. What connects layer 1 to layer 2 and layer 3? With full waveform inversion, we finally see all these feeders. So it really is quite a revolution. The central image is a derivative of the velocity model to show you what a pseudo-reflectivity image would look like. And on the right-hand side, you see a map view of layer 2, where we can see quite important linear features which connect layer 1 by the injector to layer 2. And we see a linear feature LF and SF, which is the source feeder. We see two faults controlling the flow around the injector, but we also see CO2 migrating along a channel margin here. So actually, most of the connections are sedimentary, but a few of the lower features in the deep part of the plume turn out to be faults. And there are no chimneys, which have been speculated. So what I'm going to do in the main part of the talk is take the seismic data, both reflection data and full waveform data, and turn it into assessments of storage efficiency and occupation of the pore space. The fundamental thing is how much of the pore space is used by the CO2. And I start off by using these analytical solutions proposed by Norwegian and Celia for the expansion of a CO2 in a continuous horizontal layer. And if you do that, you get a very elegant, simple geometry where the expansion of the plume is controlled essentially by the viscosity ratio of the water and the brine. But that's a little bit too simplistic, and this one neglects gravity. So what we've then done is said, okay, let's have a more general measure of the occupancy of an expanding cylinder or elliptical cylinder, the EC quota, and then scale it by swept area and swept volume. And we know the swept area and the swept volume from the seismic data. So then we can really explore how efficient the storage was. And this is the answer. This was published a couple of months ago in Greenhouse Gas Journal. So this is the fraction of the pore volume occupied using different measures as a function of time. At the bottom, you have the classical measures, which is how much of the total pore volume is used by CO2 for that expanding cylinder. And the answer is 1 to 5%, depending on the size of the box you use. So 5% is for the elliptical cylinder, tightly connected around the plume, and 1% is just for a box around the storage unit. Is that useful to Maxine and the other people doing regional mapping, Sergey? Maybe. If we scale it by swept area, we get the blue curve, which is about 10% pore occupancy. And then what's really interesting, if we scale it by swept volume, we get about 50% pore occupancy, which is the green curve. Now, this is all for mobile phase CO2. Seismic inversion is only telling you about the CO2 in the mobile phase. It cannot detect CO2 dissolved in the brine phase. So in the orange curve, I've also deducted CO2 that's slowly dissolving into the brine phase just to get the maths right. And then finally, I've just shown here the maximum CO2 saturation is possible due to capillary pressure. And we used a capillary pressure curve here to sort of invert to work out what is the possible maximum saturation. And it's interesting that the observed layer saturation at around 50% is below, but consistent with pore scale analysis. So all of that is based on map data from reflection seismic. So then we said, well, okay, but Ricardo's done this lovely layer by layer inversion of the velocity model. So let's apply our volume coefficient to the full waveform inversion data where we can analyze each layer. And the vertical line is the whole plume analysis, and the dots are the layer by layer analysis. And what we see with the layer by layer analysis is that round the injector, we have a very compact plume and looks like viscous dominated. Layer 2 has complex flow dynamics because of those faults, so much less efficient. Layer 3, more efficient, and then as you migrate up through the stack, the efficiency gradually reduces, and I interpret that as more and more controlled by gravity forces. So viscous forces are quickly decaying around the well, and the whole system becomes gravity dominated as you go up. Yeah, summarizing the same thing, and we have evidence for why that behavior is like that in the bottom part of the plume. So then comes the next step in technology. Now, an interesting thing about Sleipner is that this survey was collected by the geophysical companies. It wasn't on order by the operator at all. It was geophysical companies saying, let's try our technology at Sleipner. So they put ocean bottom nodes at the seabed, and Ricardo presented this on Monday, and that enabled a much, much better full waveform inversion because you don't have the problems of the water column, the multiples, and because you have your three-component geophones on the seafloor, you can extract high-frequency information. So this is the same workflow, but with a better data set and processed to 70 hertz, which is a very, very high degree of processing using a lot of high-performance computing. And this is our velocity model of the 9-layer plume, which I'll just play as a movie. And you can see that the main layers are very, very flat. And in the bottom part, just by the well, we see a sort of subvertical feature, which we think is this fault-controlled source feeder going from the injection well up to layer 2. And then layer 2 is quite diffuse. And then you find, as you go up through the layers, quite thin connectors between each of the layers. So we now know what the feeder to each layer was. We knew about 4 or 5 of those feeders from the time-lapse reflection data, but now with this full waveform inversion with high-quality data, we can see all the feeders. And if you're not 100% sure about that little connector in the middle here, for example, what you can do is you can play around with the thresholds to confirm that that really is a feature. It's not just a processing artifact. For example, this possibly could be a processing artifact. But when we do that thresholding, we convince ourselves that those feeders really are there. And a lot of the feeders were actually suspected from reflection seismic and now confirmed by this analysis. So they're not fiction. The vertical exaggeration here is about 5. So, you know, it was even flatter in reality. So finally, we thought, well, let's do a little bit of mass balance. And we had a presentation of this on Monday, which was met with some resistance, perhaps. But the interesting thing is that here we can see exactly where the CO2 is. So we know the volume of the CO2. So what Ricardo did is he said, well, let's be realistic about our geophysical processing, and we have an uncertainty there on the volume of CO2. So it's 155 million cubic meters plus or minus 90. We have a good estimated porosity, so we constrain the porosity quite well. And the saturation, we initially constrained by the capillary pressure model to say we have objective independent information on the saturation. And then we also assumed an average CO2 density for the whole plume using gravity inversion data and modeling data. So the other parameters have independent information, okay? But all of them have uncertainty. Indeed, they do. And we came up with the forecasted mass from FWI inversion of 19.6 plus or minus 4, which is a bit higher than the actual mass injected, but pretty good. And if you look at our Monte Carlo analysis, our mode is even closer to the right answer. Now, we're not saying that seismic data is the ultimate thing to predict mass in the ground. We're just saying the technology has moved so that we can actually get a credible estimate of how much CO2 is stored underground. Or you could say, well, we know how much CO2 is stored underground, so let's reinvert back to the saturation. So if I say I don't know the saturation and I do know the mass, then I can invert back to my saturation estimate is between 40% and 65%. And those are the saturations in the velocity object imaged by seismic. It doesn't mean there are not other saturations, lower saturations elsewhere that we don't image, okay? So that is really interesting. So we've now got a prediction of the saturation from seismic. And you could say, I know we've got some modelers in the room. It's nice to compare back to fluid simulation. This is Equinor's latest published simulation of Sleipner in it's a result from 2020 with history matching with a very high resolution model using a thermally coupled simulator so we get the thermal density effects included in the model. It's very hard to history match Sleipner, but all I want to point out is that the operator that knows the site very well got a pretty good history match. Look at their saturation scale from the forecast from seismic. It's from 60% maximum down to 30% minimum in each layer. Very close to our forecast from seismic. So that is a very, comforting validation of our fluid inversion from seismic. And finally, this is just hot off the press. I thought, well, out of curiosity, why don't I apply this simple metric to Snøhvit? At Snøhvit, we have a much poorer quality seismic data. It's a deep site with more noise. We also have pressure from seismic as well as saturation from seismic. So, but from the saturation from seismic estimate, we can also make a simple ellipse and analyze the storage efficiency, and we come up with about 6% storage efficiency at the Snøhvit 2 buoy. And by the time of the 2011 survey, which actually had lower confidence in imaging, we're somewhere between 6 and 10%. Now, Snøhvit has a high pressure. It is more fault constrained, and our excess pressures were of the order of 6 to 8 megapascals of overpressure. So this is very much more viscous dominated than Sleipner. But still, we're getting interesting numbers between 6 and 10% for Snøhvit. I will stop. So to summarize, thank you. Poor volume occupancy at Sleipner shows that the macroscopic storage efficiency is in the range of 1 to 5%, and the elliptic cylinder gives 5%. And CO2 saturation within each filled layer is 30 to 60%, not 90%, by the way. Our full waveform inversion is giving us lots of insights, and I've just listed them there. In particular, we can see the feeders, the vertical features that are controlling the CO2 migration. And from the physics point of view, we can see that decay of viscous forces to gravity-dominated forces, which will be also important for fluid simulation in the future. And then implications for regional mapping, well, that'll be controversial, I know. But just to say about E numbers, Bachu, back in 2015, said E should be between 1 and 10%. I think I still agree with him. I think he was very foresightful, and I think that's controlled by flow physics. The Norwegian CO2 storage atlas uses a range of 0.8 to 5.5, depending on whether it's a confined system or an open system. And as I've just shown you, the storage efficiency at Sleipner is 5%, if you want a number. Thank you.